Theoretically, animals' energy budgets can be quite simple, but in reality, in nature, they can be very complicated. They can be affected by wind, air temperature, position of the sun in the sky, and a host of other things. Here we will introduce you to some of these other things. As you watch the video to follow, here are 2 questions to keep in mind. What are the many ways animals can exchange heat with their environments? And what are the many ways animals might control heat exchange with their environments?
Even though the thermal energy budget of an animal or plant can be expressed as a simple balance of heat inputs and heat losses, an animal's interaction with its physical thermal environment is a little more complicated. To understand the concept of the operative temperature, we should understand what those physical interactions are. So let's diagram them out. Foremost among them is the air temperature itself. This can influence heat exchanges between the body and air through convection, the tendency of heat to be transferred between the body surface and air. The magnitude of convection heat exchange depends upon the difference of temperature between the air and body surface. The greater this difference, the greater will the transfers of heat by convection be. Also, the sign of the temperature difference matters. If the air is warmer than the body, surface convection will drive heat into the body, warming it up. If it's cooler, convection will draw heat from the body, bringing the body temperature down. The main point about convective heat exchanges is that these will always force the body temperature toward the air temperature. Convective heat exchange also depends upon the thickness of the boundary layer at the body surface, a layer of relatively still air that forms over the body, or in the case of plants, a leaf surface, as air flows past it. Generally, the larger the animal, or the longer the leaf, the thicker will these boundary layers be, and convection heat exchanges will be lessened.
One of the important factors in determining the operative temperature is the effective convection, and the effective convection depends upon wind speed. The faster the wind speed, the greater will be the convective heat loss from any object, and that will reduce its operative temperature. One of the important things we need to consider is something called the boundary layer variation of wind speed. The boundary layer variation simply refers to a vertical variation of wind speed from the ground surface up. Specifically, wind speeds down close to the surface are typically lower than wind speeds up in what's called the free stream velocity. And this means that the effective convection is going to vary upon height off the ground. Now, in order to demonstrate this, we've come to this beach on the west coast of Namibia. We've come to a beach because this represents something like a natural wind tunnel. We have a nice steady wind coming off of the ocean. The sand, as you can see, is nice and flat, and so the wind here is fairly well behaved. Now, in order to demonstrate the boundary layer, we're going to use this device here. This is a very simple anemometer. It consists of a little ball that floats up and down inside of a tube. Wind flows past, generates a suction pressure, and pulls that ball upwards in the tube, and that tells us what the wind speed actually is. And we're going to measure wind speed at 2 different heights. We're going to measure it up here, about 2 meters high, and then we're going to measure it down close to the ground, and then we'll have some comments on that. All right, so what I'm going to do is I'm going to hold the anemometer up. The wind is coming from this direction right here, and right now I'm reading a wind speed of about 9 miles per hour. Now we're going to convert that into meters per second, as you can see here off to the screen. Down here close to the surface of the ground, we can measure that just by putting the anemometer right down here. Now, it's actually not measuring it right at the surface. The actual wind speed that's being measured is at the top of this red tube here. But if you look at the height that the ball is coming up to, it's on the order of about 3 miles per hour. About 1/3 the wind speed up at about 2 meters above the surface of the ground. Now, the reason this boundary layer variation of wind exists is because of a transfer of momentum from the moving air down to the ground. The ground is immobile, but the air is moving and has momentum. And as the air moves over a solid surface, you get a transfer of momentum from the air down to the ground. And that transfer of momentum translates into the variation of wind speed. Now, if we had done several different measures of the wind speed at different heights above the ground, we would get a graph that looks something like this over here. You get a very steep variation of wind speed with distance above the ground, close to the ground, and as you get high up off the ground, it gradually converges on what's called the free stream wind velocity. So when you're talking about operative temperature, you have to be very careful to specify at what height above the ground that object is. And we'll see some examples using ground crickets of all things that will illustrate for you how boundary layer variation of wind speed affects operative temperature in an ecologically significant way.
Conductive heat exchange also enters into the thermal energy budget. Generally, this will be important to animals or plants that have large areas of contact with the surface, such as the ground. Conduction heat exchange requires contact, as we saw in our little demonstration of Benjamin Franklin's famous experiment. The magnitude of conductive heat exchange will also depend upon the temperature difference and upon the area of contact between the body and substrate. An animal lying down on the ground will have a large area of contact and therefore a large conductive heat flow between the body and the ground. An animal standing on its feet, on the other hand, will have little area of contact with the ground, and conductive heat exchange in that circumstance will be low. The really complicated part of the thermal energy balance involves radiation heat exchanges. One obvious source of radiative heat exchange, of course, is the sun, which streams energy into the earth at a rate of up to about a kilowatt per square meter of surface area. Any animal or leaf that intercepts this beam will absorb heat from it, and the rate of absorption will depend upon how much of the beam it interrupts, the so-called silhouette area, and the absorption or reflection of the light. Absorption of solar radiation can be direct, that is, intercepting the solar beam directly, or it can be indirect, diffuse, or reflected from various objects in the environment, like the ground, clouds, plants, and other objects. Another significant source of radiation heat exchange involves light that is not visible to the eye, so-called infrared or long-wave radiation. Every object in the environment that has a temperature greater than absolute zero will emit infrared radiation. The magnitude and the wavelength of this infrared radiation depends upon the object's thermodynamic temperature. For an animal standing in an environment, it is emitting radiation at fairly long wavelengths, but every object around it is also emitting infrared radiation. What determines the overall effect of this is the net infrared radiation energy balance, that is, the difference between infrared radiation emitted and infrared radiation absorbed from other objects in the environment. Usually, these net exchanges of infrared radiation are fairly small, but they can be quite significant under certain circumstances. So, for example, on a night with a clear sky, everything on Earth radiates long-wave infrared radiation to the cold night sky. This, as a rule of thumb, produces a sky temperature that is about 20 degrees Celsius below air temperatures. But remember to express these temperatures in kelvins in any calculations that you make. If a warm body emits radiation to this cold sky, its net losses of radiative heat will be quite large. That's why winter nights are so cold here in Namibia. However, if the atmosphere is warm or there's water vapor in it, the atmosphere itself can emit fairly substantial quantities of long-wave radiation that can be absorbed by animals or other objects in the environment, warming them up. Finally, the sun emits a substantial quantity of so-called shortwave infrared radiation. The sun, obviously, is very hot, about 6,000 kelvins or so. The light that's emitted from the sun is largely emitted in the visible spectrum, that is, light that we can see with our eyes, but there's a substantial quantity of light energy contained in infrared wavelengths that are slightly longer than the visible wavelengths of red. Any object in an environment that absorbs infrared radiation will absorb quite a lot of this energy. One of the interesting features of most animals and plants is that they are almost perfect absorbers of this shortwave infrared radiation. So these are the various types of physical thermal interactions that determine an animal's thermal energy budget. It's quite complicated, and this raises a question. If we want to understand how an animal fits into its thermal environment, we should strive to understand how all these various kinds of heat exchanges are integrated to produce a single environmental temperature.
Here's another level of complication which you should be aware of. Heat exchange by conduction and convection are both linear processes. That is to say, heat flows are driven by straightforward temperature differences. In the case of convection, for example, heat flow is proportional to the difference between the surface temperature of an animal and air temperature. Linear relationships such as these are intuitively easy to grasp. In contrast, heat exchange by radiation is proportional to the difference between the fourth power of the temperatures of the heat exchanging surfaces. For example, if a leaf has a temperature, let us call it T sub leaf, and it is exchanging heat by radiation with the sky at temperature T sub sky, the rate of heat exchange will not be proportional to the simple difference of temperatures. Rather, it will be proportional to the difference between the temperatures raised to the fourth power. We don't really want to get too deeply into these complications here. So to learn more, we suggest referring to this article in Wikipedia. Here is the address. Although we have mentioned biological fitness, we will not discuss it in much depth in this series. Fitness is a very important concept though, so we also suggest that you brush up on it. Here's an address where you might start. Okay, let's now turn to the practical matter of how to measure operative temperature.